also structured in a way of how you would also want to do it either in the lab or eventually on site. So first what we want to do, and what was also published, if you scan the QR code you go to the publication of this grinder device. And what we did here was make these 3D printed modules where one part fits on the drill. We have two grinding parts. They work a bit like a pepper grinder, but there's inside here there's a sieve, and I can show it to you. There's a sieve in here with a certain particle size, and the particle size is very important for extraction of the toxin. And how well you extract the toxin also is determined by the particle size. So we have three different types of sieves. This one is the largest, and you can imagine the larger the sieve, the quicker you can grind a certain amount of material. So this one was the fastest, 2 grams per minute. The others are a bit slower, but they might be of importance if you want to go towards smaller particle sizes. This one is actually close to what you would also find for reference material, the size. Yeah? So what we then did was, together with Stefan, make a lot of these modules, grind a lot of material with this largest sieve, do also an extraction in here, because here you see the small bit, it's this one, but you can also attach a larger bit, then you grind all your stuff in here, 10 grams, you close it with a lid, shake for 2 minutes, I think, if I believe the LFD protocol from Roma Labs. You shake, you get your extract out, and you apply it on the LFD following their protocols. So this is just an asset to what was already there from Roma Labs. And what we then see if we compare the LFD data to the LCMS data is that they are quite similar. The only thing is that the LFD that was used, it has an internal calibration. And the internal calibration is made for particle sizes that are more close to this one. But you can imagine if you give the LFD to a person on site and you don't give him any grinding instructions, he might use a coffee grinder, he might use a pepper. We don't know what the person uses, and because there's an internal calibration only for one very small particle size, you get major deviations because we don't know what the user in the end will do. So this device is a bit more targeted. Okay, how can the user in the end with the LFD do this grinding in a more harmonized, standardized way? Yeah? So if you want to have more information, please just ask me or Stefan, or go to the publication and we will have some demos after. Then if you have your extract, we want to do the immunocolumn part, because in the end for IR we need to be selective for the mycotoxin. So when you have your extract, you can apply it to the immunocolumns. Now this is an immunocolumn. You apply 2 milliliters of your extract to such an immunocolumn. In this layer there are the antibodies. They capture the column, and I wash the column so that all the other matrix components, like the carbohydrates, the lipids, the proteins, they are washed off, while the analyte is retained here. Then for eluting, you use 1.5 milliliters of methanol. Antibodies don't really like methanol, that's why they release the captured analyte again. And this is what we, just hang it in here, you can use this stand for that. That's what we elute in an Eppendorf tube. And then you have your purified extract with the DOM molecules in there. And then what we do is we insert a paper tip. So you insert a paper tip in your eluted volume, and then you wait. Yep. Just wait for all the solvent to have wicked into this paper tip, all the way up. And then all the particles, they accumulate here in the paper tip area, which you can see it here a little bit better. It's blue food dye, very high concentration of blue food dye, just for you to see how it works. And then most of the analyte will be accumulated here in this small area of the paper tip. And what you then do is put the paper tip on the ATR crystal, you press it and you analyze. That's it, that's the method. Now, here on the poster, what you can see if you go from the column to the paper part, so the enhanced part, we have a very nice device for that. And you can give it a 2D structure and it will cut it exactly in that way for you. So it's not only confined to just paper tips, but you can cut paper in any size you would like, because there's more and more options for that, of course. And now in this graphs, you can see a bit how the method works for a standard DON solvent. So what I do is concentrate different concentrations into this tip, and then you get a concentration dependency in this carbonyl peak that I showed you yesterday, if you remember. Now there's the concentration dependency, but because it's convoluted with the water peak that's always in paper, there's always a little bit of water in paper, and IR is quite sensitive to that. We do a second derivative deconvolution, and you separate basically the water band from the carbonyl band, integrate this area, get quite a nice calibration curve. That's how it works for standard solvents. Then if we do the entire method, there's always a little bit of matrix left, but still we can find back this very tiny carbonyl peak of the DON being this molecular identifier. And this is what we measure, and then here the gray line is a sample that has no DON, so it shouldn't really give here a peak in the second derivative, while when there is DON in there, higher or lower than the maximum set by the EU, you will see that we start to see a peak here. The more DON, the more the peak you will see. So we are working towards simplifying this method because you have here your paper tip and you have to wait, but for a rapid test we cannot wait endlessly. So we want to, in the future, I'm working on that now, use a cartridge, a card like this, where we have papers inside. And this is a rubber that I 3D printed. We want to press the papers with this rubber very tightly with some screws. And then what I do is, instead of letting the eluent into this Eppendorf tube, flowing the eluent directly into the cartridge and applying compressed air, and then you enhance or speed up this evaporation process. That's work in progress, to simplify it also for the user. And then we also try to transfer the methods that I made to the nice devices made by the team, to be able to also measure the DON or the ocotoxin or whatever analyte you want to use on paper by their devices. So this is why they made the stamps, but they will tell you more about that.
Yes, so that we developed two devices, the MiFi device and the Hi-Fi device. One device is based on the IC-LED or exchangeable light. With exchangeable light source, you can exchange it for the black body emitter. Then we have a zinc selenide crystal and the line array detector with the linear variable filters. As well, we develop a pressure stamp to interface the paper microfluidics on the crystal and to analyze the xynivalenol in the commodities. This device is meant for fast screening during the transportation storage scenarios. And the second device is a Hi-Fi device, and it's based on the tunable laser, thin film waveguide, MCT detector, as well as pressure stamp to introduce the papers developed by Anouk with the xynivalenol on it to also conduct confirmatory analysis, for example, in external laboratories.
So, what you need: wheat. This is non-contaminated wheat, okay? And we have here the first two parts, the top two parts that you should see here. So you can screw them together, like so. Now here's the drill connection, like a typical drill connection. And then there's the first part of the grinding part, which is a teeth-based grinding part, which will connect in the next part, but I will go into that later. So what you do is you just throw a bit of, normally I would use a spoon, but we just go like this. Not too much. And you keep it upside down, otherwise everything will fall out again. You can leave it, and then we make the next two parts together, which is the other grinding part, which has the blades in here and the sieve. And we can connect it to the either the collection part here or the bigger collection part if you want to go straight to extraction. Now, as you can see in this black blade part, there's a little hole. What this does for us is if we connect it with the other grinding part, there's also a little hole here. And by connecting it like this and then turn, now it's stuck because there's an internal locking system here. So now is the time to do this. We can leave it for a bit, and then you. I haven't done this in a while, so let's see. So you connect it, and then you grind. The important part is that you don't press the drill very hard into the rest of the bits because they are turning and there's crushing, so don't be strong, just hold it and press this button, and that's the only thing you need to do. Like this. And then what we did, or Stefan and me did, was do this for 5 minutes, and then you stop, you dislocate it, and then at some point you will have 10 grams in here, you add, if I believe, 25 milliliters of water, a buffer bag, you shake. I can show you how this works. You just unscrew it, and you add all the water, the buffer bag from the whole protocol Roman Labs already has available. You put the screw or the top in here and you shake it, and then at some point, after 2 minutes, you can get your extract out and do the LFD. Right? So about the paper-based part, I cannot show you too much because then we would have an ATR, FTIR, we have to go to Stefan's lab, and there's mycotoxins involved, so we decided not to do that. But like I already showed you here, you can see, you can watch it later yourself, how this accumulates in the tip area just by evaporation. And also for this, there's again a pictogram card with this connection piece. Now there are 3, you can do 3 at the same time. But if you would want to do 6 at the same time, we can just extend this and you can do it at the same time. Because the only thing you need to do is apply your extract, 2 milliliters, let it drip through by gravity. Then when that's dripped through, you add water, 5 milliliters, let it drip through, and then you elute with the methanol. This part takes maybe 10 minutes for all 3 of them. It's not super difficult, I would say. Then you have your eluent, insert the tip and wait, and then we go to the IR and analyze it. The difficult part is not really the doing of the sample prep, but it's the data analysis behind how to measure the mycotoxin on the paper. This I cannot really demonstrate to you, but the paper or the publication about this is hopefully submitted today, so I'm hoping you will be able to read it in a while, how this exactly works.
Prototypes, and okay, we were talking a lot about technical background, what is inside this black box, but imagine now you're the user and you don't care so much what is actually inside. You just need to analyze your commodity and see how much deoxynivalenol is present, and as a user you don't need to think about it. So there is a software developed by our partners, Iris. It looks like this, so there is some information, the metadata you can write about the sample, for example, the country of origin, batch number, which commodity, food type, and some comments that you want to save for the sample. Then you just need to press measure a background, and you see that background is collecting. It is very fast, the measurement itself is very fast, and you will know when it is 100%, then the ground is done. It is done, it means you can analyze your sample. So as we said, we will simulate, so it's not real DON samples. Imagine we pre-concentrated deoxynivalenol on paper, and And then you position the paper on the top of the waveguide after your background measurement. And then with the pressure stamp, you apply the pressure until you reach good contact with the waveguide. And then you can write the name of your sample, 1, 2, 3, 5, and then what you need to do, you just capture a spectrum. So the idea that at the end we will have a software developed for different users. Right now it's more like for scientists, because at the end you get your IR spectra done on paper. So you will see your spectra, but for the untrained users like farmers or someone who's not working in the laboratory, it will be implemented a traffic light, a green or red, which will show the user if the sample is contaminated or not. So the user does not even need to understand the infrared spectra. So that's it. This is whole measurement, less than 1 minute everything.
So for the hi-fi device, well, first of all, I would like to show you a bit what is inside the box. So to open it, and you will see what are the main components or the skeleton of this device. So it has this laser developed by NanoPlus. As you see here, it's a very miniaturized laser. It is just this is the heatsink box, so it's just the drivers and the heat dissipation. But the laser is just this, what you see here. Compared to other lasers like Meerkat or QCLs, which are more or less the size of this box already and really heavy, this new laser developed in the PHOTONFOOD project allows us to miniaturize the device and to have a really compact optical system. So as you can see here, it just consists by two different mirrors which focus the light to the waveguide. As you see, this is also the sensing element, and the waveguide in this case is smaller than for the MiFi. It's just a 10 per 5 millimeters waveguide and 6 micron in thickness. So in this case, the paper, which would be interface with the sample preparation from Anouk, can be even smaller, and it's just placing the paper tip here in the sensing element and also recording the measurement. In this case, we also developed together with the pressure stamp. It's a pressure transducer installed here, so you can also measure the amount of pressure you're applying on the paper, so that for reproducibility it's also enhanced thanks to this pressure transducer. So also the measurement, from the measurement point of view, it's also similar. We have the software developed by NanoPlus, for which you also can introduce your data, the sample name, and the batch, the type of food commodity, and other data. So in this case, the measurement is a bit slower. You also record the background before, and it takes around 3.5 minutes to record the whole spectra, as it is a tunable laser. So it is tuning around these wavelengths, as you see here. The range is between 1700 and 1640 in wave numbers, and this was developed according to the main Don Carbonyl group, so that we have data points in this wavelength, it's 1682 or 83 inverse centimeters, so that then we can see Don detect directly Don on paper thanks to these data points. So here is just tuning the laser by it was a programmed lookup table, so that it's introducing different currents and temperatures, so it helps this tuning of the laser. So it's basically this. Just to mention that this, as presented Paulina before, we also developed calibration curves not only for paper but also for liquid samples. So this pressure stamp can be also removed and place also liquid samples or films. So basically, well, we need to wait a bit that the background is measured. And this is more for high fidelity, so the result it will bring will not only focus on screening, like maybe MiFi is more intended for screening as a screening method, but also for confirmatory analysis with the direct dawn quantification with anode preconcentration. So now the background is recorded already, and we would place the sample on the top of the waveguide, the same as with the MiFi device. And we would also screw the pressure stamp until the optimal pressure would be reached. Once it is located the sample, just introducing sample name and capture spectra. So it will be repeating the same step, this time with the sample, and it will automatically calculate your absorbance spectra that you will see it in the screen. After that, it has different settings like uploading models already there. So it can have a direct response if the sample is contaminated with DON or not, according to the data calibrated before. So now it will be just waiting again for the process, and then you will have the data log with all the measurements done on that day. So you can also upload the spectra there and see, compare them also in the different samples.